Hi everybody, we're solving statics problems. Our topic, two-dimensional force systems. Find the point where the line of action of the resultant of the two-dimensional force system consisting of four forces and two couples applied to the plate, shown in the figure, intersects the GH line. Yes, now we have a force system. Since all the forces lie in the same plane, it is two-dimensional. How many forces consist of this force system? Let's see. Let's number the forces. Let's call the 200 newtons force F1. Let's call the 120 newtons force F2. Let's call the 80 newtons force F3. Let's call the 60 newtons force F4. The number of single forces is 4. Let's say N equals 4. There are 4 single forces. Of course, there are also force couples. 2 are given. Let's call the force couple with a moment of 42 Newton meters, M1. Let's call the force couple with a moment of 40 Newton meters, M2. The number of couples is also 2. M equals 2. There are 2 couples. Actually, this force system consists of 8 forces. N plus 2m equals 8. But some of these 8 forces form couples. 4 of them form 2 couples. Okay, now what is required of us? Returning to the question, we are asked to find the point where the resultant's line of action intersects the GH line. If we choose the x and y axes as shown in the figure, and make point G coincide with the origin, the point we are looking for is located on the x-axis, and if we find the x-coordinate, we will have found the location of the point we are looking for. In other words, we are looking for x. We are looking for the x-coordinate of this point. Now, let's look at what the resultant of this force system is equal to. We learned that if the resultant of a two-dimensional force system is not 0, we can reduce that force system to a single force. So how do we find the resultant? We find it by summing the forces. Which forces are we summing? All the forces. As many forces as there are, we add them all. But we said there were 8 forces. Some of these 8 forces are not taken into account when calculating the resultant because they form a force couple, and we can do without them, because they cancel each other out. There's no point in adding one of them and subtracting other one, the forces that make up the M1 force couple. Therefore, summing the single forces is sufficient. We find the resultant by summing the single forces. On the other hand, we know that the resultant is equal to the sum of the rectangular components, which is also R equals Rx plus Ry. Now let's use Varignon's theorem to solve the problem. What did Varignon's theorem say? It said that the moment of a resultant about a point is equal to the sum of the components' moments about that point. We can choose the point where we take the moment arbitrarily. We can take the moment about any point we want. Let's take the moment about point G. The moment of the resultant about G is equal to the sum of the components' moments about G. We're finding the moment about point G. The moment of the resultant about G is equal to the sum of the moments of the rectangular components about G, and it is also equal to the sum of the moments of the other components about point G. To find the moments of the rectangular components about point G, we shifted the force along the line of action, moved it to where it intersects line GH, and there resolved it into 2 rectangular components. In this case, since Rx's line of action passes through G, it has no moment. It only has the moment of Ry. The moment of Ry is equal to Ry times x. The moments of the other components about point G are also equal to this. There are 8 components. We'll add their moments and set them equal to this. Now, let's first find the moments of the rectangular components. Only Ry has a moment anyway. So, let's find Ry first. We know that Ry equals total Fy. The projection of the resultant on y, Ry, is equal to the sum of the projections of the components, that is, the 8 forces on y. Ry equals F1y plus F2y plus F3y plus F4y. What happened to the other 4 forces? They form a force couple, so there is no need to include them here. Now let's find the y components, or vertical components, of these forces. The vertical component of F1, or 200N, is downward. We see from the figure. Therefore, it is negative, minus 200 times sine 15. The angle it makes with the x-axis is also given as 15 degrees. Therefore, the y component of F1 is equal to minus 200 times sine 15. Let's move on to F2. Let's find the y component of the 120 newtons force. It is also equal to 120 times sine 70. But it is also negative. Since it is downward, it is also negative. F3, 80 newtons force. It's parallel to y, as it is. Its y component is equal to itself. Since it points downward, it's negative, minus 80. F4, 60 newtons horizontal force. Its projection onto y is 0, because it's horizontal, perpendicular to y. Thus, we found Ry. We get Ry equals minus 244.5 newtons. Ry is negative, so it points downward. Its magnitude is 244.5 newtons. Let's show it in the figure. What did we say? We'll take the moment about point G. The moment of Rx is 0. There's no need to find Rx. Ry had a moment, and we found Ry. Now, we'll write the moments of these rectangular components on the left. We said Rx has no moment. The moment of Ry is 244.5 times x. But since it's clockwise, it's negative. We put the minus sign in front of it. Let's move on to finding the moments of the other forces. Let's start with F1. When finding the moment of a 200 newtons force about point G, we use Varignon's theorem once again. We resolve the force into its components, the vertical components, and add the moments of these components. The horizontal component of the force is 200 times cosine 15, which creates a clockwise moment. Therefore, it creates a negative moment. The moment arm is 520 minus 50. The vertical component is 200 times sine 15, which creates a counterclockwise moment. The moment is positive. The moment arm is 50 millimeters. If we look at the moment M1, the couple, we see that the moment of a couple with respect to all points in space has the same value, the same direction, and the same magnitude. We know this. Therefore, the moment of a couple with a moment of 42 Newton meters applied to point F with respect to point G is also equal to 42 Newton meters. It is in the same direction and with the same magnitude. In other words, it is positive 42 Newton meters. Since the units of the other moments are Newton millimeters, I convert 42 Newton meters to Newton millimeters to make the units compatible. Therefore, it becomes 42,000. Let's move on to F2. Let's write the moment of the 120 newtons force about point G. We use Varignon's theorem again. We resolve it into vertical components. The horizontal component 120 times cosine 70 creates a counterclockwise moment, so it creates a positive moment. The moment arm is again 520 minus 50, so 470 millimeters. The vertical component 120 times sine 70 creates a clockwise moment, so it creates a negative. The moment arm is 240 minus 50 millimeters, so it is 190 millimeters. Let's move on to the 80 newtons force. The moment arm of the 80 newtons force is 640 minus 50, so 590 millimeters. Its moment is also clockwise, so it is negative. Let's move on to the 60 newtons force. The moment arm of a 60 newtons force is 180 minus 50. Its moment is also clockwise, so its moment is also negative. 60 times 130. Finally, let's come to the moment M2, the couple. Its moment is also counterclockwise, so it's positive. Even though it's applied to point H, we know that the moment of a couple about all points in space is in the same direction and has the same magnitude. Therefore, the moment of this couple relative to point G is plus 40,000 Newton millimeters. Let's substitute that in. Thus, we've calculated and added the moments of the other components about point G. Let's add them. From here, we find x. By performing the necessary calculations, we obtain x equals 259 millimeters. After solving this problem in this way, let's change the point where we take the moment. Let's take the moment about another point. Where should we take the moment? Let's take the moment about the point where the resultant intersects line GH. Let's call that point K. Let's take the moment about point K. Since we're taking moments about point K, the moment of the resultant will be 0. Therefore, the direction of the resultant won't concern us. We won't need to find the x component or y component. We won't need to find its direction or magnitude. Let's do it now. The moment of the resultant about point K is 0. Therefore, the sum of the moments of the other forces about point K is also equal to 0. The left-hand side is 0. Let's write the right-hand side. We'll write it as we did before, but the moment arms change this time. The moment arms of the horizontal components don't change, because point G and point K are on the same horizontal plane. Therefore, the moment arms don't change. Only the moment arms of the vertical components change. The moment arms of the vertical components also change by an x digit. The moment arm of the vertical component of the 200 newtons force has increased by an x digit, and the moment arms of the other two vertical components have decreased by an x digit. Yes, from here, we get the same result. We get x equals 259 millimeters. Goodbye.